Welcome. This video is going to talk about Planck's work with the quantum and how Einstein joined in on that work and made some further extensions. So the first thing to talk about is the photoelectric effect. And you can think of the photoelectric effect as kind of being the opposite of atomic emission spectra. So atomic emission spectra is the light that's emitted by atoms when they have energy. And then the photoelectric effect is defined as when light shines on a metal and causes the electrons in the metal to move. And so if you change the intensity or frequency of the light, you can change the number of electrons ejected and the speed they're moving at. And this is what you know as solar cells, like the solar cell on a calculator, photoelectric cells on things that turn on and off automatically, like street lights at night or maybe a night light in your home. That's all based on the idea of the photoelectric effect. So here's a picture showing what happens. So a beam of light hits the metal surface and electrons get ejected or move along within that metal, and that's the photoelectric effect. Atomic emission spectra, as we've talked about earlier, is basically the opposite process. If a gas is heated, it absorbs energy, which can cause some of the electrons to be excited or bumped out to the next energy level. These excited electrons are unstable, so eventually they emit or lose the extra energy and drop back to their original level. And I like to think of this as like a lava lamp. And some of you are probably too young to know what a lava lamp is, so you might have to Google it. But the lava lamp, you have this blob of lava in the bottom, and as it heats up, smaller blobs break off. They have enough energy, enough heat that their density decreases, and they float up to the top. And then they sit up at the top, they lose that extra energy, and they sink back down to the bottom. And that's kind of what's going on with these electrons. As energy gets put in, they get bumped further out. It takes more energy to be in that position, so eventually they bump back down. Or you could think of this like, kids at a playground. You run around for a while, and then you need a rest, so you go back to the bench, sit down, catch your breath, then you get up and you run around again. So this process repeats over and over as long as energy is put into the gas. So atomic emission spectra is defined as the frequencies of electromagnetic waves emitted by an atom of that element. So each element has its own set of frequencies, its own colors that it emits. And so it's kind of like a colored barcode, and it allows us to identify elements by this colored barcode or their spectra. And I've included a small graphic here of the spectra emitted by Betelgeuse. This is actually its absorption spectra, which we will also talk about. But it allows scientists to identify the different gases and elements that different stars have, and identify, maybe what stage of life a star is in, etc. So it certainly has a lot of application in various sciences. So Einstein realized that the wave model couldn't explain the photoelectric effect or the atomic emission spectra. He looked at the work that Planck did with the idea of the quantum, and he said, there's a particle nature to light. It's not just a wave, but there's also particles in that wave. So light is really a stream of these tiny little particles, and these particles are bundles of energy, and he called them photons. And in fact, a photon is defined as a massless particle that carries a quantum of energy. So you can see why the energy of a quantum and the energy of a photon would be equal, because the photon is the particle carrying the energy. The quantum is that minimum amount of energy. So really pretty interchangeable, thinking of photons and quantums as being virtually the same thing, at least for what we're doing with it. And that is how Einstein got involved with Planck's ideas and the quantum model.